You can hear me, right? Yeah. So this is today we will be talking about implementing optimization, uh, preferably mixed integer linear programming and heuristics for generating optimal scheduling and blend plans of raw material consumptions for a copper processing plant. Since there are too many uses of optimization, this one model that we implemented in Adani Enterprises Limited, do have similarities with procurement, with operations, with blending, and there are other things that we have mapped into this one single model, which help us to optimize on our inventories, on our financial planning, on our blending, and at the same time on our procurements. There are too many constraints that we actually handle by using this model. And we can go forward where I can tell you about more about what is the business problem and how we have arrived at a solution, which we are still implementing. So the benefits or the potential benefits are still yet to be materialized. So we can move forward.
So about myself, I am the founder of ORMAE. Before opening the company, I worked for did my master's and PhD in operations research. In the US, I worked for Amazon, Penske Logistics, and Genesis on a lot of complex optimization problem. So I've been using Groby from since 2010. In the US itself, for some of the company, we used to use Groby. And then 7 years back when I opened the company, then we used even more for many of the customers. I'm also Guinness World Record holder in mathematics. So we have done around 100 plus projects using optimization and data science. And today, the project which we did with Adani Group will be getting into a little bit more details. Akash Deep come from the Adani Group, and he'll telling his background. So Akash.
Yeah, so before jumping on to the problem description, let me just give you a brief overview about Adani and Adani Group. So we are a huge group in India. We have 7 listed companies spanning from infrastructure, cements, roads, and energy, green energy, power plants. And now we are getting into the metals and minerals space, where we are first developing our first copper smelter and refinery plant in Mundra, which is located on the coast of Gujarat. And then we will be having multiple metal processing plants in the state of Odisha and elsewhere with respect to aluminium and other things. So that's about the company, and we can move forward. So let me just give you a brief overview about the problem for the company for which we are solving the present problem, which we will be showcasing today. So we call it Kutch Copper Limited. It's a copper complex which do have many plants in it. For example, sulfuric acid plant, precious metals recovery plant, and copper smelting, copper refining, and oxygen plant. All these plants are part of one plant, which actually produces copper cathode, and then further downstreaming is done to produce copper rods and copper tubes. So this is an overview about the company and how we are using optimization is by generating daily blends, or we say at a more granular level, generating blends by using different raw materials. The critical raw material to any copper industry is actually copper concentrates that we source from different locations, geographies. So India is not very much rich with respect to copper concentrates. So we source it from Latin America, Australia, and Canada. All these things that makes it a more complex exercise because the production is continuous and we have to bang on our procurement strategy, which is optimized with our operations. So by using Gurobi and MILP, we have worked out a model which will be implemented after we will commission the plant in 2024. We can move forward. So let me let me make you understand that how systems and how different verticals in a copper plant works. So, for example, the first thing that we need to do is we need to source few concentrates which further to be mixed together, because a plant is not designed in a way which aligns with a single concentrate in the available in the market. But at the same time, we need to source concentrates. It is just like a chocolate factory. Different cocoas uh, mixed together to maintain the quality, which gives you the same taste. At the same time, different concentrates sourced, and they are mixed together to come to a feed, which is aligned with my smelter or furnace. So a furnace is something that processes this mix of concentrates at first, and it has a lot of metallurgical reactions. So we need to be careful about what we are actually mixing together. Each concentrate, if I'll say, do have some elemental characteristics with respect to it, and on the basis of these to be mixed, which is captured by the minimum and the maximum ranges per meter ranges. So we design rates with the feed rates, which are predefined. That's a range. And then we need to minimize our wastage, because we do not have enough space in my warehouse, and each concentrate, each quantity of concentrate worth billions of dollars, right? So smelter operation settings is something that I was talking about. If there are E1 to EN specifications with respect to each concentrate, then in the feed it has to be some E1 min and EN max for each, right? And we can move forward. This is schematic about it. Now, Doctor will take over with respect to solution methodology.
Thanks, Akash, for explaining the business problem. So Akash is from the Adani Group side, which taking care of, that the best optimization practices are able to actually help the business. So he's really close to the business. So now the two different approaches were planned. First is determining the both blend plan and the procurement plan using MILP, so mixed integer linear programming. Second is utilizing the mixed integer linear programming to determine the blend plan and subsequently generating the procurement plan heuristically. So the first approach, the complete problem is modeled as MILP. So concentrates characteristics, design specs for elemental loading. So then we get an optimization output, which is blend allocation and blend consumption. And then there's a reporting, procurement plan inventory, tens of concentrates. So the challenge in this approach is complexity due to size of the problem. To mitigate, a rolling horizon technique was adopted. Both the solution time was still around 30 minutes. So it had 515,000 continuous variable and 95,000 integer variable for a 6-month model. Other disadvantages are to generate blends, combination of raw materials to be consumed at a granular level, wastage of concentrates. Do you want to comment on the disadvantages?
Yeah.
Akash.
When we first build the model, let us talk about the acceptability of the models. Since process industries are majorly worked out by humans, and it really takes a lot of challenge to on the acceptability of the models. So when we first implemented the first solution and got the results for each day, we were getting some kind of blends, but at the same time, since we were looking at around 320 billion combinations, out of which the most profitable one aligned with my operating parameters, procurement parameters, and logistic parameters, all those things, the blends were jumping like anything. For a plant manager, if on one day I will say run blend 1, on second day I say run blend 2, it will be a toll on them with respect to mechanics of the plant. So for resolving that problem, we use the other approach, in which we first define the stability of the blends. So the blends became more stable, and at the same time, only the concentrates that were getting exhausted one or more, like two more concentrates getting exchanged with some others, but more or less the concentrates remain the same. Only the one that gets exhausted, those were getting changed. And in this particular approach, we got more benefits with respect to it.
So now the second approach, the best blend is created using the MILP model. That's where we are using Kurobi. So the MILP model generates the best blend at the moment based on the present stock available. And then the solution goes to the heuristic side. The heuristic would run the best blend till one of the concentrates get depleted. And updated stock based on the consumption and procurements is shared with the MILP model to generate the next allocation. So compared to the previous approach, the second approach took less time, only 5 minutes for solutioning. So the second approach was chosen over first approach for solution design.
Yeah, because the solution set, the entire possibility frontiers get reduced. Because in the first approach, it was the entire combinations that the model was looking, and in this, only a subset of it the model was looking. But yes, at the same time, giving me solutions which are even larger. Earlier, the decision variable with respect to blend that I was getting and procurement, both the things, it was 365 days for 1 year. As doctor mentioned in the previous slide, there were 15,000 continuous variables. That becomes 1 million, more than 1 million continuous variables when I plan it for an entire year, right? And at the same time, this model needs to run each day, because each day a market changes. It has market driven variables into it as an input variables like prices, cost, and the terms which are typical in a metal processing industry. So that's how it makes sense to move to the next approach, which is giving me solutions in just 5 minutes. That's what we emphasized initially, and that's what we got finally.
Yeah. So now let's look at the methodology deployed in the second approach. So creating a blend plan. So concentrate selection, assign consumption quantities, take care of the design specs, optimize for maximum earnings. That's what the blend plan is created. Blend allocation, which is a heuristic, allocate the created blend until at least one of the concentrate is exhausted. So concentrates can exhaust at any time. Make procurement decision for concentrates that have not been made in the last 45 days. Maintain inventory levels. So basically, so the MILP approach is used in the creating the blend plan, and the heuristic approach is used in the blend allocation. Want to say something?
Yeah. So if I would like to make you understand it clearly, let us just assume that I have some concentrates with me as a data point. Say I have some C1 to Cn concentrates, and out of that, as a business problem, I need to select few. For example, I need to select n which do have multiple values in it. For example, 5, 6, 7, 8, or 9 concentrates to be used in my blend. And at the same time, each of these concentrates can be consumed on the quantity basis. The second thing that you find when we say create blend plan, first it do a concentrate selection. So out of n, it selects some m concentrates in a particular blend, and these blends changes so that number of concentrates going into a blend also changes. So that is also a challenge. And then it gives me an optimum quantity of each concentrate to be used in that particular blend, and that's how we get, like, it creates all the possibilities with respect to each number of concentrate that goes into the blend, and then it assesses what each blend is, what earnings each blend is giving, then ranks it up, then selects the one which gives me the highest possible earnings, and then starts my my production with that particular one, and starts make changes to it as soon as things gets exhausted in the heuristics.
Yes.
Yeah. So I'll just make you understand now what are the constraints that we are using. So one of the constraints we have is with respect to the blend design, right? So each blend can have a number of concentrates into it, not more than some value, let's say n. And at the same time, with respect to each with respect to a blend, I do have around 22 characteristics of my feed, which also defines my concentrate when I mix it up. So each of these characteristics should be in some min and max values, right? And then I need to, the concentrates that I selected, I need to select it in such a manner that I can get it in my warehouse with a lead time. Since I talked about that, none of these concentrates I can get on a ready basis. Like I order it today, I'll get it tomorrow. It's not like that, because they have to be sourced from overseas, different geographies. Just for example, take an example of some concentrates getting transported from Latin America to India. So it will take around 45 days. So I need to plan 45 days in advance for getting that concentrate in my warehouse, so that I can run my optimal plan that I forecasted when the year started off. Right. At the same time, we do have integration of systems with respect to live tracking of vessels. It's just like Uber. You have drivers, we have vessels, and when we do have ETA, which aligns with my next 7 days or 10 days plan, it gives me a plan. It also considers not only the things, the concentrates which are in my warehouse, but also which are still sailing, which are in the vessels which are sailing and near to my port. So we have a facility in Mundra. It's a Mundra port. That's ours, and that's how we source and import our material. Then at the same time, I cannot source a concentrate with any parcel size. So it has to be in a predefined parcel size. At the same time, it is not homogeneous for every concentrate. For example, there are two concentrates, C1 and C2. The lead time can be different. Like it says 45 days uniformly, but it can be different for some 60 days, for some 45 days, 15 days. So that's how the problem becomes even more difficult. At the same time, the parcel sizes, for some, it can be 10,000 for 10,000 tons. The others, it can be 20,000 tons. And then we do have capacity per day. For example, each concentrate, the feeder that we have, it can only be blended with certain min and max things that we have, and we have only limited space in our warehouse. So all these things to be mapped together, looked upon, and then create a blend plan which do satisfy my procurement, my consumption, and my inventory, and my working capital requirements. So that's it about the constraints.
So now the modal features. So the maximization of revenue. So maximization of earnings due to blend plan and procurement plan. Optimal blend plan with procurement and inventory management. That's the optimal solution. Speed. So faster model building. Now the new approach gives takes only 5 minutes. Faster solving time. Detailed analysis. So KPIs analysis, blend composition analysis, base storage analysis, consumption analysis. This is one of the most powerful benefit of optimization, that you can run a lot of these what if scenario, see exactly what better could have been done, in different ways, not just on the current actual settings, but also the adjust other settings. Multiple scenario, analyzing multiple scenarios, flexible to change in arrival of certain concentrates, study impact of decisions.
So that's how I would like to just particularly talk about the things that you see on the right, detailed analysis and multiple scenarios. So this is one thing that helps the managers, the plant managers and decision makers to understand that how this optimization technique is working out. They don't understand a whole lot of maths, but we need to give them the solution in a manner that they can actually consume. So that's how we do it, through these KPIs analysis, building dashboards, creating graphs, generating files in a format that is most suitable for them, and at the same time allowing things to allowing parameters to change whenever they want, and whenever the market condition changes. And these are the most important things which makes the model flexible and getting accepted by the industry, right? So on the business impact, if I'll talk about, so we are still not ready with our plant. We are yet to commission our plant in 2024, but we are building this model because it requires a lot of time. Only after 3 years of operations, we will get to see the full impact of this optimization model. So after 3 years, when my plant will stabilize on all fronts, we think there will be 20% reduction in my cost, or say 20% gain with respect to my entire revenue generation. And the model, since model is can give me solution in less than 5 minutes, so it becomes handy, and it has multiple applications with respect to sales and operations optimization that we will be implementing soon. And again, since there are a lot of decision makers which works on this one particular thing, it's not one person deciding. There are some blend managers, procurement managers, operations managers, then top management involved. So this ability to run multiple what if scenarios for strategic investments and other things, that makes it potential and a really good solution and optimization for particularly for a metal processing industry. In this case, we are doing it for copper, but it has immense applications in metal processing industries.
So this was the project which we discussed in the detail for the Adani one. These are other additional optimization and data science projects which we worked on, kind of. So I think we can now open it to questions, particularly related to the project which we discussed.
Do you achieve the same result after the 5 minutes optimization than with the 30 minutes optimization? So with your new approach, or is there deviation in the target function?
If I talk about the solution, the target, the objective function, it even improved this time. And the kind of solution that we were seeing earlier, there were a whole lot jump arounds with respect to blend. Now it became more stable, but solution with respect to operating parameters remains the same, but the objective value improved.
Because the focus was on very specific problem of creating the blend plan. The blend allocation, which was anyway dependent on exactly what is available and a more of a heuristic procedure. That's where we went.
The reason being in this improvement in the objective objective thing was that earlier the model was selecting the most optimum blend as the first blend, but at the same time when it used to select the second one, it was selecting a suboptimal blend which was far away from the first one. In this solution that we are doing, second approach, it just modifies that first one. That is why the objective value improves upon. I hope this answers your question.